So my name is Erica Redline. I am a principal member of the technical staff at Sandia Labs. I work in the organic materials science group, and I'm here to talk to you about our technology of fluid infused elastomers for improved high temperature performance. So this work was actually funded by a Sandia Tech Maturation Program. It was a pretty short duration, low dollar amount project just to kind of do a proof of concept on the technology. My co-inventor is Mark Grubelik, who has since retired. He worked in the geothermal group prior to his retirement. A little bit of background on why we're interested in this. So at the time, we were working on evaluating commercial off-the-shelf elastomers in simulated geothermal environments to understand their degradation pathways and get an idea of their lifetimes. And the reason that we're interested in that is because these geothermal wells currently sit at around 150 degrees Celsius, but there's a push to move them towards hotter and hotter temperatures, approaching now 300 degrees Celsius. And so elastomers, rubbers, are not something that you typically think of being in such a high temperature environment, but they perform some really critical functions like sealing, so for zonal isolation. They also are used as seals to protect really expensive electronics that they put downhole to monitor the wells. And typically what they use right now are elastomers based off of fluorocarbon polymers. So that's just polymers that have carbon and fluorine as the primary chemical constituents. These are very specialty materials. They can be quite costly. So just as an example, I'd like everyone to take their thumb and their index finger, touch them together, and an O-ring of about that size costs over $100. Compare that to just your typical elastomer O-ring that you could go to your local hardware store and buy, which would be about $1. So they're quite expensive. Typically what will happen, especially at the downhole electronics monitoring, those O-rings get replaced every single time that equipment goes downhole, because if they fail, that is a lot of downtime. Now, if something larger like a packer or a sealer fails, now you're talking about costing upwards of $1 million a day because you've really shut down production for the day. So if we can improve the lifetime of existing materials, we could have a really big impact on geothermal technology, perhaps make it even more competitive with non-renewable sources. Now, I mentioned we were looking at the performance of commercially available O-rings and how they behave in different simulated environments. And you can kind of see the need for why we need better performance just from these pictures here. So I have them clustered by some different aging conditions that we subjected them to. The 5 different O-rings are just 5 different materials. So you can see on the left, the materials aged in brine, they tend to get scaling. So the different elements that are downhole in those wells tend to accumulate on the surface that can impact sealing force. And the thermally cycled conditions, you can see we had catastrophic failure of one of the materials, some other failure where materials just flaking off in another case. Then an aged in drilling fluid, we had an O-ring fail, like a chunk broke off, and we have the surface there just flaking and breaking off. And so the surface is critically important here because that's what's providing the seal. So if that's flaking off, that's not a good thing. And so, when we're thinking about this, actually, this is kind of funny that Mark came up with the idea because he's an explosives expert and I'm the polymer scientist of the team. But Mark said, why don't we try to infuse these things with this high temperature inert oils that I'm working with for just a different project. And so the idea here being that we take a typical O-ring, we subject it to those elevated temperatures and oxygen, which is a really main driver for polymer degradation. You get failure. But we thought, hey, what if we try infusing with these fluids, subjecting it to the same conditions, and let's see if that, gives us any improvement. And so why do we care about this? So I mentioned, this is really useful for geothermal technology as we're getting towards hotter and more efficient wells, but really anything that involves high temperature, high pressure, or very harsh chemical environments could probably benefit from this technology. The nice thing about it is that you don't have to change anything about the formulation, right? You don't have to go back to the compounding manufacturer and redevelop a process to put in some kind of additive. You can just take something off of the shelf, use our process, and get an improved performance from it. So some other areas that we thought might have interest in using this technology: oil and gas exploration and production, Brayton cycle systems, concentrated solar, petrochemicals, automotive industry, and just in general, elastomer or O-ring manufacturers who could use this technology and then upsell their polymers. In terms of the market, nearly 60% of the world's elastomers are used in automobiles and cycles. That includes tires and automotive parts. There's a lot of O-rings and seals in high temperature, like steam environments in automobiles. There's a plethora of other applications, including architecture, medical products, sports products, resin modification, and things like that. Globally, the market closed at $71 million in 2020 and is expected to grow at a positive compound annual growth rate of 6% through 2025, with the automotive segment being the driver of most of that growth. And in particular, when I talked about these specialty elastomers, fluorocarbon rubber, FKM, also known as Viton, that one is believed to will be growing by 4% through 2024. So there is a pretty big market for that. We also think we might be able to find some use in the medical market, depending on some future research that we have ideas for, and I'll discuss that in a bit. So I talked about the technology, where we think it might be useful for. Now let me show you the data demonstrating that the technology works. So the first thing I'm going to talk about is in the upper left corner here. This is known as compression set. I'm just going to explain what this test encompasses because it's a little counterintuitive if you just look at the values. So to do this test, we start out by measuring, in this case, the diameter of our O-ring. We'll apply a compression and keep that compression on as we age the material. When the aging is done, we take off the compression and then we remeasure the diameter of the O-ring. If the diameter is the same as what it started from, that's 0% compression set. If the diameter is flattened and to the same value that we compressed it to, that's 100% compression set. So lower is better. If you look at the table at the bottom, I'm showing examples of compression set for 4 different materials that we tested. You'll see in the first column, the compression set with no oil versus the values in the second column, which is after we had oil infused them and aged them. The values are all lower for the compression set with the oil infused materials. And you can visually see that here. And so this, in this case, this was an X ring, so it has an X looking cross section. But when we infuse it with oil, you can see that it hasn't shrunk as much versus the one without oil. And it's pretty dramatic difference that you can see there. Another thing that we like to look at is how the physical properties change. So you saw some of those O-rings had material flaking off, which is indicative of a brittle type degradation mechanism. And so one thing that we can do is we can measure the stiffness of the material as a function of the cross section. So modulus is just kind of another way to talk about stiffness. And what we're looking for is basically no change, right? If the material is getting more brittle, then the modulus values will increase. There's another degradation mechanism that could be apparent where the chains are actually getting chewed up and broken down, and then you'll see a decrease in the modulus. And so these are the graphs on the right are simply 2 different types of elastomers, of fluoroelastomers. And this is modulus as a function of cross section, where 0 is one edge of the O-ring and 1 is the other edge of that O-ring. What you'll notice, and what I want you to compare is the dashed value, which is just the straight up O-ring, nothing's been done to it. The purple squares are the untreated O-ring after we've aged it. So you see there's a significant increase in the modulus on the edges for both materials that we investigated. And you'll also notice that if we look at the stuff that was oil infused and aged, which are the green circles, the green filled circles, we're really not seeing much of a change there. We get maybe a slight increase in the modulus at the corners, but really nothing nearly as dramatic as we're seeing with the untreated materials. And if you want to know a little bit more about why we see that kind of U-shaped profile, we can talk about that in the breakout session later. So with that being said, I mentioned that this was a pretty low dollar, short duration project. So we never really optimized the process at all. So what you're seeing on the last slide, those dramatic improvements, is just we kind of threw stuff in there and tried something. It worked great. We never had the opportunity to optimize. And so we think we can optimize for a series of fluoroelastomers. So those specialty elastomers for about $150,000 over the course of a year. That helps us mature the technology a little bit further. We think that if we get an additional funding, about $300K instead of $150K over the course of 1.5 to 2 years, we can start expanding our applications, maybe partnering with someone for tech maturation. Instead of testing in our simulated environment, we could test maybe in an actual environment. That would be a lot more useful data. And so with that, I will conclude, and I am happy to take your questions.
Thank you for the presentation. This is Beto Payares, and I have my starting question is, I was really shocked a little bit by the market size you presented as $71 million.
Mhm.
How did you arrive as that as a market size on a global basis? And just to be very transparent, it seems like a small opportunity for, in this case, what could be venture financing.
Right. So I actually relied on the business development people to look at the market for me because it's not, I'm a scientist. I don't really look at that area. So we're thinking, more like specialty elastomers, so a smaller subsegment of that. I'd have to talk to the person who helped me find those numbers and see where those were derived from. Um, but I mean, if you think about like the geothermal industry, they're about $8 billion globally. And I know for the specialty elastomers, it's probably maybe like 10% of that. So it's, or maybe a percentage to 10% of that. Yeah, I'm sorry, this is just not my forte in terms of the actual market share, but I can certainly talk to someone who's in that area and get back to you.
Yeah, Eric, this is Mike. I just want to build on Beto's comment. I think when we look at companies to invest in, we want to see about $100 million market minimum that the company could capture in the short term, which implies a much larger market overall. So I think the question he's asking is quite important because that this might lead you down the path of, frankly, licensing and partnering with a corporate development arm of a company that would want to get into the elastomers market versus raising capital on your own. And it probably also would lead me down the path of advising you to think about the funding you need right now coming in a non-dilutive funding and perfecting the product and then building out the market potential while you're doing that to hopefully see something larger that might be able to be invested in and or has a valuable opportunity from a licensing standpoint.
Okay.
So Beto, maybe I'll just ask one more question while I've got the floor and I'll turn it back over to you. Can you just talk about the sort of the readiness of the technology? It sounds like it's fairly early, and maybe just give us a little bit more sense of what are the major steps that you need to take to advance the technology further.
Right. So we have the technology demonstrated in a lab environment. So it's a TRL. I think that's 5. What we're looking at is really understanding how far do we have to infuse the oil to have a positive effect? Is it a millimeter? Is it a micron? We don't know at this point. What other fluids might be helpful? We need to look at, how long does the fluid stay in there? Is it just stuck in there? Does it leach out over time? Things like that. And I think, if we wanted to get even a more scientific understanding of it, we can look at things like what are the oxygen diffusion rates into a fluid-filled elastomer versus just your typical elastomer.
I think we have time for maybe one more question. Okay, if that's
sorry, Mary, I had one more.
Mike.
The muting is sort of funny because it sends me back on mute, then I can't unmute. Sorry about that. There's a little bit of delay. Erica, just one more question on as you look out over the next handful of years and you secure some funding, what's the IP landscape look like for the company, and then what does the IP landscape look like for players that are already in this marketplace?
Right. So we have patented the technology just for the overall concept of fluid infused elastomers. And we specifically made that pretty broad. There might be, some additional work understanding the mechanism a little bit better. We could have additional IP generated from there. I know you mentioned, licensing this. I think probably the easiest thing to do would be to license it to one of these specialty O-ring manufacturers just to implement along the line for maybe a more high dollar, product that they can sell. But yeah, I think we're pretty good in terms of what we had secured for what we have tested with our initial patent, but there could be some stuff as we progress to optimize.